We are looking at practice test number 4. Module 4 contains chapters 8 and 9. Chapter 8, hypothesis testing. Chapter 9, inferences from 2 samples. And we start with chapter 8, hypothesis testing. A test of hypothesis is always about a population parameter. It is important to know on a normal basis, we don't have access to population. We are interested. And since we don't, we have to deal with sample statistics. The observed value of a test statistic is the value that we calculate for a sample statistic. As the sample size gets larger, both type 1 and type 2 errors decrease. Type 1 error is rejecting a true null hypothesis. So rejecting a null hypothesis when it's true is also known as false positive. The probability of making type 1 error is equal to alpha. Type 2 error is failing to reject a null hypothesis when it's actually false, and that's false negative. Alpha represents the probability of making type 1 error. Beta is probability of making type 2 error. 1 minus beta is called the power of the test when we make the correct decision, probability of rejecting a false hypothesis. All right, let's look at some examples.
In 1990, 5.8% of job applicants who were tested for drugs failed the test. At the 0.01 significance level, Statistic claimed that the failure rate is now lower if a simple random sample of 1,520 current job applicants results in 58 failures. Does the result suggest that fewer job applicants now use drugs?
Whenever we do statistics, in essence, we are doing word problem. When we do word problem, it is important to understand each and every part that is given. So 5.8%, that's a percentage, that's a portion. So if you pick an applicant, either or, it's a binomial distribution, and there are 2 outcomes. So the percentage that failed the test is 5.8 because we either fail the test or we don't. Alpha is 0.01, N is 1520, X is 58. Therefore, the very first thing we want to do, we want to write the given. We are dealing with the binomial distribution where N is 1520, X is 58, P is 0.058, alpha is 0.01. When we look at the test of hypothesis, in general, there are 4 steps. We have to find H0 and H1. H0 is the null hypothesis. H1 or HA is the alternative hypothesis. We have to write the claim and tails where it goes. The tails is always next to H1, the claim we have to figure out. Then we calculate the test statistic. We come up with the critical value using alpha. And then we make a decision. Decision has 3 parts. We either reject or not. That means fail to reject H0. That is all we do with our calculations. Then what does it mean? The claim becomes true or false, and then we restate the decision. And in this case, we want to pay attention to this lower in a moment. So all of this really are the steps that we need to take. So P is equal to 0.058. Therefore, we can calculate the Q, that it's 1 minus P. We have to check to make sure an NP and NQ are large. So clearly, when we multiply 1520 by 0.058 is larger than or equal to 5. And of course, when we multiply it by Q, it's even larger. We also need P hat, which is lowercase x over lowercase n, which ends up being 58 over 1520. And we use a bunch of decimals to represent that. Now we are ready to actually do the test of hypothesis. Before we do that, whenever we deal with proportion, the test of hypothesis, test statistic uses this formula. You do have a formula sheet. You can use it with your exams, as you know, and you need to know what is the test statistic formula. Z equals P hat minus P over the square root of PQ over N. Therefore, we are going to do this by rewriting the information we found from the previous page. P, Q, alpha, and the p hat that was calculated. First, we start with H0. P is 0.058. H1P is less than, because of this lower, 0.058. This is the claim. This is what we are checking. And because it's less than, it's left tail test. The second step is to calculate the test statistic. So we go through the process. We already have everything we want. So we want P hat, we want P, and then the square root of PQ over N. We use a calculator. We end up with negative 3.309. That is the test statistic. Critical value comes from the choice of alpha, and the table or technology that you use. Remember, you're using the Z table. With proportion, you only and always use the Z table. So alpha of 0.01 results in negative 2.33 or negative 2.325. If you do the drawing, notice that this separates the rejection region from the non-rejection region. So if this is negative 2.325, negative 3.309 is way into the tail or the rejection region. Again, non-rejection region, rejection region. Because the number is way into the rejection region, you are going to reject H0. Now, rejecting H0, let's just look at the first step. You are rejecting H0 because of what happened. When you reject H0, that means, loosely put, you are accepting H1 or HA, the alternative, and therefore the claim becomes true. Now, if the claim becomes true, you just rewrite this. There is sufficient evidence to support the claim that the failure rate among job applicants for drugs is now lower. Results suggest that fewer job applicants now use drugs. Now, what did we use here? We used what is known as traditional method. So I want to make sure we understand what happened here. In the case of a traditional method.
How did you get that Z equals to negative 2.33?
This is from the table.
Oh, from the table. Got it.
Yes. You can take it from the table or technology, either way is fine. In the case of a traditional method, you compare two numbers. What do you compare? The critical value, which separates the rejection region from non-rejection region, and the value of test statistic. Because the test statistic is way into the rejection region, you reject H0. All of your calculation results in number one and number one only. The rest is up to you to do the writing for your readers. This is traditional method. The second method is using the p-value. What is the p-value? It really depends whether you're looking at the left tail test or the right tail test. In this case, because this is a left tail test, so your first step says is a left tail, and you found your test statistic to be a negative value, the area to the left of that is compared to alpha. I'm going to discuss that in the next page in a moment, but just while I got you here. So the area to the left of that compares to alpha, and the two areas tell us the answer. Because the area to the left, as you can see from here, of course, we're going to look at the p-value in a moment, is less than alpha, we reject H0. So again, traditional method, we compare two numbers. What are the numbers? Test statistic versus the critical value. Now we're going to do the p-value. I have this table for you. So first, what type of test? Do we have a left tail test? Area to the left of. Do we have a right tail test? Area to the right of that. Do we have a two-tail test? Well, if the number is negative, area to the left times 2. If the number is positive, area to the right of that times 2. That's how you calculate the p-value. Therefore, for us, we found the test statistic to be negative 3.309. The p-value is the area to the left of that test statistic. So area to the left. And that's 0.0005. Remember, you are picking this from the table. You use a calculator. However you do that, that is fine. Needless to say, technology gives you a better answer. In any event, so the p-value compares what? the area to the left of your test statistic, because it was a left-tailed test, to alpha. Since it's less than that, we come up with the same decision. What was the decision? Reject the null hypothesis. So there is nothing brand new. We should get to the same result. As far as type 1 error is concerned, remember we defined type 1 error as rejecting H0 when it's actually true. Therefore, the type 1 error for this example is rejecting the claim that the failure rate of job applicants who were tested for drugs is 5.8%, when the percentage is actually 5.8%. Probability of type 1 error numerically is equal to alpha, which was 0.01. It was given in the question. Also, if you were to use the TI calculator, remember you have to justify your work with your steps. But ultimately, as far as picking up the numbers, here's the process. I have it in a TI calculator command in the last module. We have it here. And if we go through the process, 1 proportion z test, we put x and n, and we highlight less than, we do the calculation, and it results in what you see here, negative 3.309. That's what we had calculated. Of course, this is negative 3.31, you can say, or 0.309, and you can change this to 6, so on and so forth. Of course, the reason the number is slightly different because they use a lot more decimals than we do. Now, look at the p-value. I want everybody to see the p-value. This is the p-value, 4.67273554 times 10 to the power of negative 4. That means you have to bring the decimal 4 to the left. If you do the rounding, you get to the same answer. So obviously their answer is more precise. But remember, e minus 4, that means times 10 to the power of minus 4. And that means if I were to write the number, this is 4. Let's say the next one is 7. I'm doing the rounding. So you need to go to the left of that with 3 zeros. And this number, if you round it, becomes the same as what we came up with. Again, obviously, technology gives us a more precise answer. Traditional method, we compare this number, which is test statistic, which is calculated, with the critical value. P-value, we compare the area, in this case, because it's left-tailed test to the left of that, with alpha.
A sample of 54 bears has a mean weight of 182.9 pounds. Let's assume that the standard deviation of weights of all such bears is known to be 1 to 1.8 pounds at a significance level of 0.1. Is there enough evidence to support the claim that the population mean of all such bear weights is less than 200 pounds?
Again, we are dealing with word problems. So let's see what's given one by one as we come across a number. So this is N, 54. A sample of 54 has a mean of weight 182.9 pounds. So this is X bar because this goes back to those 54 bears. We are assuming standard deviation for all. That means sigma. Somehow all must be there. Normally we don't have access to that, but it's 121.8 pounds. Alpha is 0.1, mu is 200. So it's very important that you write the given. Let's go with those steps starting with H0 and H1. Mu is 200, H1 mu is less than 200. It makes it a left-tail test again, and this is the claim again. That's what we are checking. Now, one thing I want to make a point of, anytime you do the test of hypothesis, we are concerned with the population parameter only. So you never use X bar here. The second part is test statistic. So we need to know the formula we are going to use, which is equals X bar minus mu over sigma over square root of n. Why are we using that? Sigma is given, and we are dealing with the mean. Again, look at the given. All you have to do, plug in, evaluate. You get negative 1.0317, the test statistic. Critical value comes from the choice of alpha, the table, Z table. So you use the Z table, you come up with this answer, and take a look at the graph. So critical value, alpha is 0.1, negative 1.285. So take a look at alpha. Test statistic, look at the location of test statistic. And these are rough, okay? It's not precise, but it is way into the non-rejection region. So I'm going to compare the two numbers, which is the traditional method, and I'm going to discuss the p-value in a moment. So as we compare, it's way into the non-rejection region, therefore fail to reject the null hypothesis. So this is the part that comes from all of these calculations, and I can't emphasize the importance of this graph. It tells us everything we need. So compare the location. Test statistic, non-rejection region, this is the first part. Now, if you are not rejecting H0, that means you're rejecting H1, and therefore you're rejecting the claim becomes false. And you use the sentence from the question, there is not sufficient evidence to support the claim that the population mean of all bear weights is less than 200 pounds. There is not. If we were to do this by technology, and before we do that, by the way, the p-value would be this area. Here's your test statistic. So look at the green area. The green area is alpha. The blue area is the p-value. And as always, you can do it with table technology. It doesn't matter. So you use the technology. This is what you get. And take a look at the information that you put in. And the result here. And that is the p-value, which is way larger than alpha of 0.1. This is larger than alpha of 0.1. And you get to the same result, which means fail to reject the null hypothesis. So again, traditional method, compare test statistic with critical value. You compare two numbers. P-value, compare two areas. Area given by alpha, area created by the test statistic known as the p-value.
16 new textbooks in the college bookstore had prices with a mean of $70.41 and a standard deviation of $19.70. Use a 0.05 significance level to test the claim that the mean price of a textbook at this college is less than 75. Assume normal population.
So what's given? The first number, n equals 16. The mean of 70.41 pertains to those 16. So this is X bar. Those 16 have a mean of 70.41 and a standard deviation of 19.7. Those 16 have a standard deviation of 19.7. This is S, not sigma. Goes back to 16, not to all. Alpha is given as 0.05, mu is 75. So the very first thing, spend enough time reading the question to understand the given. H0 and H1, mu is 75, mu is less than 75, that's a left tail test, that's a claim. So we are checking the claim. Now, because sigma is missing, we are using T. So T equals X bar minus mu over S over square root of N. So you should know which table to use, when, and why. You have written everything, just plug in, evaluate, negative 0.9320. Critical value comes from the choice of alpha. Because it's a T, we need degrees of freedom, which is N minus 1. And that is 15. So alpha is 0.05. Degrees of freedom is 16 minus 1 equals 15. So when you go to the T table, if you use the T table, then look for degrees of freedom. Across that, you see a bunch of numbers. Now, alpha is 0.05. This is the area in one tail. 0.05 is the area in one tail. Why one tail? Because it's a left tail test, which corresponds to 0.1 in two tails. And the answer is 1.753. Because it is left tail test, you make it negative. This is the limitation of a table, the numbers that they give you. So look at the graph. Alpha of 0.1 resulted in a critical value of negative 1.753. If I'm going with the traditional method, I am comparing this number test statistic, which is negative 0.9320 here. Remember, this is 0. And it puts us way into the non-rejection region. Therefore, the result is very simple. Failed to reject the null hypothesis. So we are going with the traditional method, comparing the two numbers. Failed to reject the null hypothesis because the value of a test statistic is inside the non-rejection region. So if we don't, that means we are rejecting H1. That means we are rejecting the claim. The claim becomes false. And you can do the writing from the question. There is not sufficient evidence to support the claim that the mean price of a textbook at this college is less than $75. Now, if we were to do it by the technology, we put in the information for t-test. Here's the result, and pay attention to the p-value. Now, what is the p-value? Let me show you. Because this is again a left tail test, the alpha is the green value of 0.1. The p-value is the area to the left of test statistic of negative 0.932, equal to, according to technology, this number. .18305,304. So let's say 0.18, which is larger than alpha of 0.05. If you were to do it by a table, and I want you to pay attention to this because you really don't want to use a table, it's difficult, but you can have some idea. If you go with 15, look at the numbers at the bottom. The numbers are getting smaller and smaller. The smallest number is 1.341. Why am I looking at this one? Because this number, and remember the limitation of a table, you have to use the positive one. So this number, positive 0.9320, is less than this. So we are somewhere here. And the area is this. What's happening to the area? It's getting larger and larger. So area in one tail is larger than 0.1. So we may not know the answer from the table, but we do know for sure it's larger than 0.1 according to this. But you use a technology to get to the answer.
Tests in the author's past statistics classes have scores with a standard deviation equal to 14.1. One of his current classes now has 27 test scores with a standard deviation of 9.3. Use a 0.01 significance level to test the claim that this current class has less variation than past classes. Does a lower standard deviation suggest that the current class is doing better? Assume the population is normal.
So let's write the given. 14.1 is sigma because it says test have a score of standard deviation equal to 14.1, test scores. Doesn't say how many. One of the current ones, n is equal to 27. Now, n equals 27. The current one has a standard deviation of 9.3. So this goes back to this, that is S. Why? Symbolically, it's important for you to write it because in this case, we have two standard deviations. Which one is which? This is a population standard deviation, sigma. This is sample standard deviation, S. Alpha is given as 0.01. So we need to write this. In my opinion, this is extremely important. H0, sigma is 14.1. H1 sigma is less than that, which makes it a claim. Again, it's a left tail test. We will look at other types. But for now, this is also a left tail test, which brings us to the next step, which is calculation of a test statistic. Chi-squared is n minus 1 times s squared over sigma squared. Anytime you're doing the test of hypothesis for one sample or one population, and you are looking at standard deviation or variance, and you're comparing it to a number, this is what you use. So again, using the formula, everything you wrote here, plug in. Results in 11.311. The next one is the critical value. Comes from the choice of alpha. Degrees of freedom is n minus 1. Chi-square table, which needs the area to the right. Alpha is 0.01. Degrees of freedom is n 27 minus 1, makes it 26. This is a left tail test. We need the area to the right. So 1 minus that. So take a look at the chi-square and pay attention to the fact that we need the area to the right. Because it's left tail test, the area to the left is 0.01, the area to the right is 0.99, and I have chosen the bottom page 26. Of course, the left column has all kinds of numbers. I don't have room, I put 26, and take a look. You're looking at degrees of freedom of 26. At the top, you read the area to be 0.99, and you have your critical value. Let's do the drawing. So critical value is 12.198. Chi-squared is 12.198. Test statistic, which is 11.311, is way into the rejection region. So we are comparing two numbers. What numbers are they? The critical value is 12.198. And by the way, you remember the chi-squared is all positive values. 12.198. Test statistic, less than that, rejection region. So the first step is to reject the null hypothesis. So if you are rejecting the null hypothesis, you're accepting H1, claim becomes true, and you use the wording from the question. There is sufficient evidence to support the claim that this current class has less variation than past classes. However, less variation doesn't mean they are doing better. A lower standard deviation doesn't suggest that the current class is doing better. It just means that the grade is more homogeneous, closer to the mean. Mean value might be different, and that's important to understand. Now, let's go with a calculator and see how we approach that. If we were doing it with technology, you can calculate the p-value as follows. You want from 0 to 11.311 with the degrees of freedom of 26 chi-squared CDF. And this is the p-value, which is this area. Area to the left of test statistic because it's left tail test. Area to the left of test statistic, 0.00, let's say 6, or 0.0055. And you compare it to the alpha of 0.01. Clearly, this number is less than alpha of 0.01. You come up with the same result. Reject the null hypothesis. Now, by any chance, it's very difficult to use the table. If you wanted to use the table, you have to go here and take a look at this number, 11.311. As you look at this number, it's hard to see, but 11.311 is between these two numbers, the bottom two numbers. Between these two, it's hard to see, as I mentioned. And therefore, the area to the right is between these two, and the area to the left is 1 minus that, and that gives you a number close to what you see here. And you get to the same result of rejecting the null hypothesis.